Alrighty, folks. Hopefully everybody is doing well. We got a little short lesson today to end the week before our live session review with folks. And we're going to be talking about something known as move semantics today. Okay? And just a short warm up as we're moving into the end of week 6. Just looking forward to seeing folks come into the live session or sign up for office hours to make their introduction if they haven't already, or just ask them questions. So either way, hopefully get to see and meet some of you as we're only 1 week away from the end of the semester, if you can believe it. All right. So let's go ahead and dive into this one. But before we move on, something that we talked about last time was iterators. So two topics. Iterators were sort of our second pattern, and this pattern showed us how to traverse or access a data structure. So we saw a couple examples of forward iterators where we were basically just walking through some data structure like a vector from front to back, or and how to do that using that begin statement, whether it was dot begin or the stood begin statement. So really helpful way to show the intent to other programmers for what you're doing and how you're moving through those data structures. And the iterators really come in handy too, because we can build on them, as we saw once we learned some of the standard algorithm functions provided to us. So this is a way to almost program in, I would call it a more functional style of programming with C++, where you're trying to reduce the amount of work you're doing and sort of thinking in functions in the data that you're operating on. But we saw how iterators could be used there for different things like copying, reversing, finding all the unique elements, and so on. And that's a really cool part of C++, I think, and again, something that makes you a much more modern C++ programmer. And it's these kind of things too. I might mention that C++ gets a bad reputation for being a very old and clunky language, and it certainly has its its quirks, at least on the error message reporting, certainly. but with the algorithm library, it really lets you use it in a much more modern and nice way, and you can write some elegant code. So those accumulate functions, nth, reverse, copy, swap, all those kinds of functions are really useful for how we move and manipulate and access data. And speaking of moving data, that's something I want to talk about today in a moment. But before we do that, we have A9 that's been pushed to everyone's repository. So I'm just going to do a quick check-in on that just to show you what's going on. So A9 is again revisiting image processing. This is likely, I've been debating whether there's going to be a 10th assignment or not, maybe one for fun. But this is likely going to be our last assignment for the semester, just pragmatically to make sure that folks can get everything else done. And we sort of just end strong. I don't think we can add more assignments in the last week. So we want to just finish off with this one and call it there. All right, so just looking at this assignment, you're going to realize it's a familiar one. It's doing image processing again, but this time again with threads, so we can parallelize our code, okay? So the support code is going to be fairly similar, but this time you're going to be working with threads. And I've provided a little example of it, how to work with some threads here. You'll have to write the implementation, but we're just going to implement the red filter and the two grayscale filters, just so you get some more practice with threads and writing an actual threaded application. And the challenges are, one, understanding that if I'm changing the colors on this image, I'm doing it 1 pixel at a time. And because I'm working one thread getting access to 1 pixel at a time, I actually don't need to do anything with locks. So that makes this a nice assignment in that sense. The other thing to think about is, and I'll go ahead and I want to draw on this one just a little bit, is to think about how you access your pixels, okay? So for instance, if we have some image here, and here's the rat or whatever from the image, and we're accessing 1 pixel at a time per thread. So the question is, how many threads should we spawn? So how many threads should we create? Okay, and we could create 1 thread per pixel, that's certainly something that we could do. But if this is a, let's say it's just a 400 by 400 image, that's a lot of pixels, right? 400 times 400, you know, you do the math here, 160,000 threads. You know, our machines typically have two threads per core. So that's a lot to maintain. So there's a little bit of overhead when you have so many threads here, okay? So in a systems class, you might learn about some of these heuristics like 2 threads per core. That's about how many you'd want to do. So we need to figure out some way of blocking out this image into different sections. So that's one strategy. We could sort of divide this into a grid here. And say, well, you know, let's just divide this image into 12 or 16 pieces or however many and have threads just operate on a particular section. That would be a very efficient way to do things. But it turns out it's actually also pretty efficient if I just have this image here to actually just launch one thread per row here and just access things one row at a time of pixels. Now, why that is because for our threads, when they're loading the data for one segment here, it's actually also going to preload some of the next data here. So you get a lot of cache friendliness by doing this, okay? So that's something just to keep in mind with this strategy. So the strategy that I'm going to present to you in the lab right up, and you can see a little example in the image, is how to launch one thread at a time that's going to access one row of the image at a time and manipulate the pixels here. So you can see a little strategy for that. So I'm going to leave that to you to implement and to understand a little bit, okay? So that's going to be your task, and just the 3 image functions this time, or rather the 3 filters. Let me scroll down here. The red pixel filter, the gray pixel filter, and the gray pixel threshold. Okay, so you just have 3 this time. You can actually just as easily implement the other blurs, but we've done that, and I want you to focus on just getting the threading done properly as well. Okay, so that's it, and a little for fun experiment too, just to motivate it a little bit, is that you can actually run this program with something called time on the terminal, and if you run it, although maybe we need a better timer here, and then just do one of the filters and then close it. You could try to get a sense of how much time it takes. Actually, you probably want to use an elapsed timer, but it might be interesting to get some sort of preliminary benchmark just to see if your threaded program actually runs faster. So what I would do is look for C++ elapsed time, and this is just going to be sort of if you're curious and look at some of these examples, and you'll find some for just being able to measure the time, you know, to run your actual red filter, for example, versus your old assignment. It might be interesting to go back and do that, okay? So anyway, that's your last assignment, assignment 9 on image processing, a nice fun one to play around with, okay? So with that said, that gives us time to move into some other topics in C++. Today is going to be a little bit of a shorter one, just to introduce it so that you know it exists, and we'll see a little example. But I want to talk about it because it's important when it comes to optimizations. Okay, we're going to talk about something known as move semantics. So the idea is, you know, this isn't a course on optimization. C++ is a tool you would use to write very optimal programs. That's very likely why you know, many of you are taking this as a prerequisite. You know, even if you're not directly going to use C++, if you're using machine learning stuff, many of the libraries are still built in C++. If you're doing gaming or graphics, many of the libraries and the code itself is written in C++ because you need that performance. And C++ allows us to get that performance in the language. We have a lot of control over how we do stuff. In that sense, it's a very expressive and powerful language in allowing us to control how we work with our data, okay? So what this means is one of the areas where a lot of other programming languages run into trouble with performance is they make a lot of copies, okay? Now, where are copies made? You know, every time you pass an object by value as an argument, that's making a copy. It's going to make a full copy of that object, even if you just use it for a little bit. And some languages don't give you the choice if you want to pass things by reference to avoid copy. So C++ allows you to do that. When you create an object and initialize it, then the copy constructor is called. So, and oftentimes that could also be avoided. And you're just paying for all these little things that add up over time, especially if you're doing these in loops, like our graphics programs that are going to run a really long time. You just start losing performance very, very quickly. So I want to talk about something called move here. And move is basically a way to allow you to transfer ownership and move to another resource, okay? So instead of making a copy, if what your intent is to really move some data into some other variable, you can do that. So you actually move the data into the other data structure, and you're sort of transferring ownership. So that's really what move is. It's a transfer of ownership, and it avoids a copy because you're actually just moving or reassigning the data to a new location, okay? So let's actually look at some live examples of this so that we can make sense of what it means to use these sort of move semantics here. So I've got an example here that I'm going to write up. I'll try to write up one or two examples here, but let me just start with a simple one here for move. So the basic idea is, let's say we have some function like a swap. Now we've learned that we don't really need to implement this, but let's do a swap and let's make some kind of type here. Okay, so let's make a class here, T, and I want to define the constructor. So let me print out when the constructor is called, and I'll just put an end line here. And let's also put the destructor. So I'm actually just going to make these little one-liners here so you can see them as much as possible on the screen. And let's make a destructor here, okay? And we might actually need a copy constructor as well, okay? These are our three amigos. How do we do that? Const, the type, reference, and the copy here. So this is our copy constructor and destructor. Okay, so let's actually swap a value A with B here, okay? And let me actually just make sure that this compiles. So I made these changes, just make sure our class works. And oops, one extra tilde mark. That's why I'm always compiling as often as I can write here. Okay, so let's swap our types here. So how would we do this if we wanted to swap all of A's values with B's? Well, first thing we need to do is make this public, and let's just give it some data here, whatever it might be. Let's just leave it all public. Let's just say it holds some string of characters here. Okay, so there is actually some sort of pointer here. I'm just going to call it a string here. Okay. This is internally how a string is. It's just an array of characters. Okay. So if we wanted to do this swap anyway, what we would do is we would create one of our temporaries here. Just call it temp here. And we would want it to take on the form of, say, A here. Okay, so I'm initializing it here with A. And then I would set A equal to B, and then B equal to temp here, okay? And then we should actually implement our copy constructor, right? We would have to go through and initialize some memory and make a copy of this and all these things, right? I don't actually care if this works for now. That's it. So you can, that is a little to-do item, okay? So let's actually run this in our code here where we create some object here, A, B, and then we actually call our swap function here. So let's see. So it looks good. And if I run it, what you're going to notice is there's a lot going on here, right? We're just creating something. We're creating two things. That's our constructors here. And then we call swap though, and then you see we're making 3 more copies of our objects here, okay? Because we're making a copy here. Well, we're making a copy here when we pass it in by value, another copy here. Then we're making another copy here when we initialize our temporary, doing our swap, destroying the 3 copies, and then finally at the end of our program, when we reach main, we destroy A and B here. Okay, so we're making, we're doing a lot of work here by just passing a few of these objects around. Now, what if this isn't just a string here, and it's a vector of, even if it's integers, but this is some data here. What if I have 1,000 ints here? That's a lot of information that I have to copy here. And even for this one, which might be a more trivial data structure to copy, this could be a graph or something. All of a sudden, these copies that you're making really start to add up. But really, my intent is just to swap the data here, right? Just say, okay, A has B's stuff and B's has A's stuff now. So again, just looking at this code, we have 2 constructors called, 3 copy constructors, and then we do destroy all of our objects here, okay? So my question is, could we get rid of at least one of these copies here? And the answer is yes, we can. And this is by using the new thing, which is move semantics. So I'm going to go ahead and include a utility library here, and this is for something called standard move. Okay, and this is what's going to transfer ownership rather than create from scratch the values stored in an object. Okay, so how do we do this? Well, std_move is going to be our tool. So let's just start by refactoring a little bit our swap function here. And the trick is when we create this temporary here, we're instead just going to move in the value into temp here. And we're going to do the same thing. In A, we're just going to move in whatever the contents of B are into A. And again, we're going to just move whatever the contents are of temp into. Okay, so that's where we're going to start. So let's go ahead and try to rerun this and see what happens here. Whoops, and let me get rid of that vector here. And let's try to rerun this. So it looks like it's compiling, which is good. And if I run it, well, I still see that there's 3 copy constructors here and 2 other constructors. So 5 objects in total created. So we haven't saved ourselves anything. Now, why is this? Well, we need to actually define our move constructor and move assignment here. Okay, so how do we do that? So just a little bit more syntax here, but we're going to create another constructor, and this is going to be our move constructor, which transfers ownership of our object rather than creating a new object. Okay, so that's the idea with our move constructor here. And our goal is that this is going to inevitably save us a copy. Okay, so now the syntax here that's going to be a little bit new for us is that we're going to take the type and then 2 ampersands and then the copy that we are creating. Okay, and that says that we're going to use the move semantics. We are transferring this ownership of this object. So we're passing in a reference to something that already exists, and we're going to move the value in. Okay, so let me go ahead and show what this looks like. So what I'd be doing is I'd just be setting mstring for this current object equal to the copy of mstring. Okay, so just reassigning this pointer here. But then I'm also doing the full transfer of ownership. So my copy doesn't own anything. And I should really name this something like old here. So the old owner here, or previous owner. Now it doesn't own it, so we just set it to its default value, and this successfully transfers the ownership. Okay, so let's go ahead and try to run this. Let's see what happens. And we get some errors. It says use of deleted function and so on here because it's missing the operator. So that's actually move assignment as well. So move assignment operator. Okay, so we have this when an object's being created, but in this instance where we're using assignment and creating an object, we need to set up a move assignment operator. So we do the same sort of thing here. And it's going to be similar to how we did our assignment operators before. So the type operator equals, and then t with 2 ampersands, and then the old owner. Okay, and then this looks very similar. So if our current object is not equal to the address of our old thing, then we will proceed and do something, and then return reference, or excuse me, the actual object here. So we're going to repeat this pattern here, though, where we're just transferring ownership. Okay. So here we go. So that does the transfer of ownership. Again, my current object is taking on whatever old string is, repointing to it. Whatever the copy operation would be. If it's a pointer, I can just point to that memory. And then the key, though, again, is that I'm losing the ownership here. This is just pointing to null done. So I'm truly moving the data and just having one pointer to it here. Okay, so let me try to rebuild this. This works. And if I run it, you're going to notice we have one less constructor here. Okay, we still have our 5 destructors here because we have a temporary in our swap that needs to get destroyed, but we've removed one of our copies. And if I told you that you could go for every 5 constructors that you had, if you could go down to 4, or in other words, every 3 copies that you had, you could go down to 2. That's a 33% savings of your program. So, you know, your boss would probably give you a very nice raise if you told him you made the program 33% times faster, or 33% times less copies, which, you know, results in some sort of speed bonus. Okay, so that's the idea with move. The syntax is a little bit wonky here, I guess, in that now we have 2 ampersands, but that's what it means here, is we're doing a move and a transfer of ownership. So that's what I want to talk today about, and that's where I'm going to leave us a little bit on a shorter topic for today before our live session. But this utility move, which allows us to transfer ownership. Okay, so that's it for today, folks. Make sure you check out the live video, catch up on your assignments, and get started on the thread, and we'll try to finish the semester strong.